Okay, in this third video on gases, we're going to review Charles's law, Gay-Lussac's law, Avogadro's law, and the combined gas law. I'm covering pages 189 to 192 in your notes, the note packet I gave you, and also the summary table on page 199 you might want to look at. I'm going to go through these fairly quickly because I want to make another video that will take more time and talk about the ideal gas law, which we did not go over last year and is fairly important. So I want to talk for a second about something called a Maxwell-Boltzmann distribution. This is a statistical term, and it is a way of graphing things. So that's all that it means, silly statistical word. But when we have a Maxwell-Boltzmann distribution graph of molecules, this area, so let's take this area that's colored in blue. The area under the graph is directly related to the number of particles, atoms or molecules, present in this gas that's represented by the blue. I'm going to take a black color, and we're graphing here kinetic energy of the molecules versus how many molecules, what fraction of them have that kinetic energy. So at any particular kinetic energy, let's say here, take a low one, if we go up here to the point on the curve, that would tell us the fraction of molecules that have that kinetic energy. You can see that the highest fraction of molecules up here have a kinetic energy right there. But the area under the curve represents all of the molecules in this gas, and they have different kinetic energies. Now, when we talk about temperature as a measure of kinetic energy, we're really saying it's a measure of the average kinetic energy. So the average of everything that's under this curve is what temperature is measured, but that doesn't, but that's the average. So that doesn't mean every single molecule has exactly the same kinetic energy. Now what happens is when if we were to heat up this gas and then regraph it, which is what is done in red, you can see that it moves forward. So if it moves forward, there are, let's use this, we're going to ignore this part about this is for kinetics, but we're going to take, this is our kinetic energy here. Now when we were at the lower temperature, which was in blue, there was a small number of molecules that are shaded in blue that had a kinetic energy that was greater than this point right here. But if we increase the temperature of the gas, the graph moves forward, and we can see that if we increase the temperature, then more of the molecules will have an energy higher than this kinetic energy right here, because the graph moves to the right when we heat it. So this, by graphing things this way, it helps us understand how kinetic molecular theory helps us understand why the volume of a gas will increase when the temperature increases. Because when we increase the temperature, we can see here, then we will have more molecules with a higher kinetic energy. If we have more molecules with a higher kinetic energy, then we have more molecules that are moving faster. And if they're moving faster, they're going to hit the sides of the container with more force. They have more energy, and that will cause the container to expand. So in this way, we're trying to use kinetic molecular theory to explain why when we increase the temperature, we will increase the volume. Temperature is directly proportional. You know, I wrote that wrong on the other slide. Temperature is directly proportional to volume. And when things are directly proportional, we graph them in a straight line. The graph of a straight line you learned in algebra is y equals mx plus b. M is the slope, it's a constant. B is your y-intercept, it's a constant. Y is directly proportional to x. So you could write y is directly proportional to x, or you can put a constant in front of it and say y equals mx plus 0 if the y-intercept is b. Okay. So here we have a sample problem. This is on page 190. When the temperature of a fixed amount of gas changes from 20 degrees Celsius to 40 degrees Celsius, what happens to the volume at constant pressure? So let's circle some important things. We're looking for temperature. It's a fixed amount of gas, so we're not adding any. We know what the temperature change is. So we know T1 is 20 degrees Celsius, and T2, temperature 2, is 40 degrees Celsius. We want to know what happens to the volume. So V1 is, I don't know, and V2 is also, I don't know. And we know that pressure is constant, so pressure isn't going to factor into it. So I have a relationship between volume and temperature. It's a direct relationship. They are directly proportional. So when I write that they're directly proportional, I write, oopsies, V1 over T1 equals V2 over T2. And so now I can substitute in. I have V1, let's call V1 X, okay? And we'll call this Y. Or we'll just call it V2, okay? So we'll just leave this as V2. So I have X, which is my initial volume. Well, I could just call it V1 too. Anyway, before we do this, let's go back. These temperatures right here are in Celsius. And we need them to be in Kelvin because the effect that temperature has on volume will be proportional to the relationship of the Kelvin temperatures. So we need to add 273 here. So 20 plus 273 is 293. 40 plus 273 is 313. And I'm going to confuse you more, but I'm just going to leave these as V1 and V2. So we're going to have V1 divided by 293 Kelvin equals V2 over 313 Kelvin. And what I'm trying to find out is V2. So I want to solve for V2. So I need to have V2 alone, which means I'm going to multiply both sides by 313 to get rid of it in the denominator here. So I'm going to multiply this by 313, 313K. And I'm going to multiply this by 313K. So over here, the 313K cancel. So I'm left with V2, which is what I want to know, what happens to the volume. On the other side, only the K's cancel. So I'm going to cross them out. And I'm going to have that 313 over 293 multiplied by V1 equals V2. And I can figure out this relationship right here. I'll do that. It is 1.06. So 1.06 times the initial volume will be the second volume. So the second volume will be 1.06 times the first volume, just slightly greater. And you can see now how important it was that we change these to Kelvin, because if we had left the 40 and 20 in there, it would have looked like the volume was doubling, and that is not the case. Okay, so years ago in Italy, Amedeo Avogadro, this was back in the 1700s, observed that when you had the same amount of two different gases at the same temperature, so the same amount of two different gases at the same temperature, they occupied the same volume. And this is called Avogadro's law, or Avogadro's hypothesis. And we can write it mathematically as initial volume over number of moles equals the second volume over number of moles. So the volume of a gas is proportional to the number of moles you have. If you have 1 mole of a gas, it will occupy a certain volume. If you double the number of moles of gas, then the volume that it occupies will double. Kinetic molecular theory explains this for two reasons. One is it assumes that all molecules have no volume, which of course they must have some, but it assumes that they have none. So whether you're dealing with tiny helium or a giant molecule like argon or atom like argon, the size of the individual molecules is in theory not taking up any space. The other way that KMT supports this is that it says that there's no, let's draw some molecules in here, there's no attractive or repulsive forces between these atoms, which would, and if they were being attracted to each other, that might change their volumes if one had more intermolecular forces than the other. But we're saying under KMT, we're assuming that there are no intermolecular forces. We're going to change that when we talk about real gases in our next video. So anyway, same amount of two gases, the same temperature, you have the same volume. So if you have 1 mole of a gas, it'll occupy a certain volume. If you double the moles of gas, then you will double the volume. So we can put everything that we've learned so far together in the combined gas law, which you learned last year, or whenever you took chemistry. P1 V1 over T1 equals P2 V2 over T2. All these things are proportional. And we did not talk about how pressure is directly proportional to temperature, but there is a question in your notes, sort of a on your own question for you to think about that. It's very similar to the Maxwell-Boltzmann effect on volume. So anyway, this is called, what I've written here is the combined gas law. And if your number of moles of gas is constant, if number of moles is constant, then you can evaluate the effect of pressure, volume, and temperature. They're all dependent on each other. If you change one, the other two will change. This is called the combined gas law, and it can be handy. I'm not going to do any problems with it, but you should be able to substitute in and solve.